Okay, the first item of business. First of all, pick up the worksheet if you didn't on your way in. First real item of business. Got some good news. So this is what it says on the Canvas page for today. There was some good news. I just found out this morning. I came in. I got an email from our AP coordinator from the district and from the College Board themselves. They made a change to AP Physics 1, I guess over the break because we're just hearing about it. It might partially be due to COVID, but they are making this change permanent. And it's kind of nice because I think this is the 5th year of AP Physics 1, maybe 6th. Can't quite remember anymore. But I've always thought it was a lot, maybe just a little bit too much material crammed into a single year, which is why our pace is pretty furious as we go through this course. And why it's very difficult for a lot of students and probably translates into the reason that every year it's the lowest scoring exam out of all the AP exams. AP Physics 1, much lower average score nationwide than any other exam, even AP Physics C. In my opinion, it's because there's too much material, right, and not enough time to actually delve into it, because by the time a lot of students are finally starting to understand it, we're on to the next thing. And we have to do that because, let me tell you, as a teacher of AP Physics 1, it's a constant struggle every year to try to get at least a week, maybe even a week and a half of review time at the end of the year before the AP exam. So the thing is that the last units in this class, electrostatics, which is electric forces, DC circuits, direct current electric circuits, and then mechanical waves and sound. Those are concepts that are expanded on much more in AP Physics 2. Now in AP Physics 2, we don't have that at this school because there's just not enough people sign up for it every year, so we don't offer it here. But if you do take AP Physics C next year, the entire second semester of AP Physics C is electromagnetism, so we do a lot of electric forces, electric fields and magnetic stuff and all that stuff. That's the entirety of the second semester. But because those concepts are covered in AP Physics 2, they have decided to eliminate those 3 units from AP Physics 1. Now, mechanical waves and sound, they're not really covered in AP Physics 2, so I don't quite agree with this part of the decision. But the electric circuits and the electric forces, definitely get rid of those. They're in AP Physics 2, they're in AP Physics C, so we don't need to do them in AP Physics 1, and that will allow us to, have more time. So they've dropped units. If you look at the College Board website, they divide all the concepts that we cover into 10 overall units, and units 8, 9, and 10 have now been eliminated from the course, and they will not be assessed on the AP exam starting this year. So that means we have a lot less material to get through second semester, which means we can slow down a little bit, start taking our time a little more, start delving into specific techniques that can apply to any realm of physics, and then just take a little more time in each particular unit, which is good news. It's good news. So the pace will be a little less fast and furious. And in my opinion, this should allow us to have quite a bit of time at the end of the year to review for the AP exam, meaning that I expect the scores to be significantly higher this year. Because there's been years where if I've had like an illness that put me out for like a week, where we've had like 3 days to review for the AP exam after we finished all the material. So we'll have weeks at this point. And that doesn't mean we're going to slow down to a crawl. We still got quite a bit of material to get through, and I want to make sure we have enough time at the end of the year to do a thorough review of all the material that will be assessed on the exam. But it will be a lot more slower paced than it has been up to this point. So that's the good news. That's the good news. The bad news, we got to keep moving. So we're going to do some physics. Now to do that, though, I'm just going to kind of review, because I'm sure, maybe Brock did. I don't know. Maybe you did some physics over the break. Maybe. Oh, you did? Okay. If you didn't, if you're like me and you don't work on vacations, then you probably are a little rusty on maybe some of the work and energy concepts that we learned about before the break. So I'm just going to spend 20 or so minutes kind of just rehashing, reviewing a few of those concepts, telling you where the equations are on the formula sheet, what those equations mean and all that stuff. What you need to know that's not on the formula sheet, and just to refresh your memory a little bit, and then we'll spend the next couple days working on that multiple choice question worksheet that you picked up on the way in. After we finish that worksheet, then we'll actually do some practice FRQs, and then we'll probably test over this unit next week, sometime end of next week. Okay. All right, so this unit was all about work and energy. work and energy and power. But if you know conceptually and mathematically how to deal with work and energy, power is kind of easy. It's pretty easy. So in general, and you might want to have, because I will be referencing the set of notes that I gave you guys. If you lost those, you can pull them up on the website or on my Canvas page. But I will be referencing this. If I have an object and I exert a force on it, and in response to that force, the object moves, then work is being done on the object. The equation for work is, as written on the formula sheet, it says F parallel. That's what the two lines for, times displacement D. I prefer delta X or delta Y for D, but this is how it's written on the formula sheet, so that's what I'm going to go with. Understand that that's displacement, though. The D is displacement. And that equals, well, the parallel component of the force will always be the cosine component when you do your vector decomposition, so you can just abbreviate that as FD cosine theta. And that is if you have an object that, say you have a force that's at an angle, and then the object will undergo some displacement, D. Again, I like calling this delta X. I'm thinking in my head delta X, because that's the displacement variable that we're used to at this point, but whatever. And then there's an angle between those two vectors. That's the angle theta. This is how we determine how much work is done by this force on this object. Okay? And if you look, this is the adjacent component. The adjacent component is always the cosine component. So that's why it's the parallel component of the force. The component of the force that's parallel to the displacement is the one that does work. Some interesting angles to just take note of, to understand. The cosine of 0 degrees. So that's if the force and the displacement are in the same direction. What's the cosine of 0 degrees? Anyone know? 1. So if there's 0 degrees, then it's just force times displacement. That's it. Okay. What's the cosine of 180 degrees? Negative 1. So work can be negative. If the object is moving and there's a force on it that brings it to a stop, in this case friction forces in the axle, well, the object's moving that way, but the force has to be this way because it's slowing the object down. Well, that means negative work was done. Why is it negative? Mathematically, it's because the cosine of that angle is negative 1. Okay. By the way, if I push in the same direction that the object moves, right? If it starts from rest and I push on it and it gains kinetic energy, it speeds up as I push on it, I do positive work on it. I give it energy. If it's moving towards me this way and I push on it that way to bring it to a stop, that's 180 degrees. Right? The cosine of that angle is negative. I do negative work. That means I'm taking the energy away. If negative work is being done, then energy is being lost by the object or the system of objects. If the work is positive, then energy is being added to the object or the system of objects. And then, interestingly, the cosine of 90 is the same as the cosine of 270. What's the cosine of those two angles? 0. 90 degrees would be up. 270 degrees would be down. Those forces would be perpendicular to the direction of motion. Those forces do no work. Okay. So you can think of an object moving in uniform circular motion. Right? The force on a planet that's moving in a circle, the gravitational force is always perpendicular to the direction of motion. So no work is done on the planet. Okay? Perpendicular, so that's something you might want to remember if you don't know this trig stuff, because if you're not in pre-cal, you haven't learned this. You might have briefly talked about it in geometry, but your calculator knows it, so you can always put these angles into your calculator. But just understand that perpendicular forces, forces that are perpendicular, forces perpendicular to displacement do no work. Very often I see students that are trying, what's the force, they're trying, how much work is done, they start calculating the work, and they end up getting the wrong answer because they forget about the angle thing, and all they needed to do, there's certain problems where it's like, oh, that force is perpendicular to the direction the object is moving. It does no work. The work is zero. You don't even need to do any work there. You don't need to show any work there. Right? Okay. So that's the most basic definition of work. For those of you, I assume all of you will be taking AP Physics C next year. We'll learn the calculus version of this equation, which is a little more all-inclusive. It will actually be, you can calculate the work done by any force on an object undergoing any path through space. This is a specific, you have a force that's constant. It doesn't change. If the force changes, as let's say a function of position or function of time, then we got to be a little more careful. And there are certain cases where we can have variable forces in this class, and we can actually calculate the work done by those forces. And to understand why, I introduced force versus displacement graphs. Our first foray into the graphical physics, or depicting physics graphically, was our motion graphs. And we learned that, slopes on those motion graphs told us a physical concept, or told us a physical quantity. The areas, associated with those graphs, some of those graphs tells us about a physical quantity. Well, if I plot force versus displacement, I can just use my knowledge of geometry to come to a pretty interesting conclusion. Let's say I have a force that's constant. Say F equals 10 newtons. Well, if F equals 10 newtons and that quantity doesn't change, and I plot that, it's just a horizontal line. So say I push on an object with 10 Newton force, and over a distance of, 10 meters. Well, I can look at this graph and say, oh, well, there's some geometry there, right? I can say that the area here is equal to the base of this, which is the displacement d, times the height of this rectangle, which is force F. So I can say that's force times displacement. Okay? Well, force times displacement is work. There might be a cosine tacked on the end, but the cosine of the angle, if it doesn't change direction, that's a constant as well. So the area here is force times displacement. That's literally work. Right? So if I have a force versus displacement, not force versus time. Force versus time graphs we'll talk about next unit when we study momentum. But if I have force versus displacement graphs, we're talking work. Okay, the area underneath that graph, the area between the line and the axis is work. If it's in the positive quadrant, the first quadrant, then that's going to be positive work. Positive work being done, then you're adding energy to the system. It could very well be a negative force, right? Negative forces do negative work, so that would be in the fourth quadrant, and you would be taking energy from the system. The chair slows down. Right? And then we went from here, if you remember. If you don't, it's fine. It's been a while. We went from there to talking about work done by forces that actually vary. And when we talked about this, I just tried to give you a little bit of insight into the calculus that you'll learn next year or the year after or in college. Especially if you're going to be a STEM major, you're definitely going to learn this stuff. But let's say I have a force that varies. It varies with displacement according to some weird function, like this. I can actually, the same thing applies. The same thing applies. If I find the area underneath that curve over some distance, d, that area is still the amount of work. This area equals the work. And I try to point this out because this was one of the things that confused me when I was learning about this. It's easy to see why it's the force times displacement. It's easy to see why the area is work here because it's just force times displacement. Well, how can that be the case if we have a changing force? Well, we can approximate this area just by dividing this guy up into a bunch of rectangles. I can just do this. And then each one of these rectangles behaves just like this. Right? Just like this. It's a base times a height, which tells me amount of work done on each one of those distance intervals, displacement intervals. And then I add those areas together and I get the total amount of work done. And when you learn calculus, you learn that, well, I can actually use a process very much like this to get the exact area under any curved line. What's that?
Definite integral.
Yeah. Now, we don't do that in this class, but what we can do, if we have a force versus displacement graph that varies according to, say, some linear function, like this, the area concept still works. Sometimes it's a triangle, sometimes it's a trapezoid, which you can divide into a rectangle and a triangle, right? The area here will still be the work. Okay. So it's like on the front page of those notes. You know, you can calculate the work done by that varying force. Now you might ask yourself, well, how often do you actually find forces that vary directly proportional to displacement? And the answer is pretty often, actually. I got a spring here. And if I pull down on the spring, Newton's third law says that the spring pulls back in the opposite direction on my finger, right? And I can actually feel that. And it puts a little indentation in my finger because it's pulling up. Here, it's not a big force at all. But the more I stretch it, the bigger that force gets. Bigger stretch, that force is getting big, and I can feel it. I can feel a lot more there than I can here. And that's because the force increases with displacement, right, from the unstretched position. And it turns out that for an ideal spring, which this spring is, it's like an ideal gas, there's no truly, purely 100% ideal gas in the universe, but there's gases that behave largely ideally. This spring behaves largely like an ideal spring. And an ideal spring, the force is directly proportional to the distance of the stretch. And you'll be surprised when you take AP Physics C next year how often you see springs in the real world, in engineering and in just the real world in general. So yes, we get force versus displacement graphs where they're linear pretty often in physics. Okay. Anyway, so again, you can get the area, or you can get the work done by a force on an object by just looking at the force versus displacement graph for that particular process. Cool beans? Okay. Now, this is kind of indicated on the formula sheet because really the work equation as indicated on the formula sheet says delta E equals W, which is work, equals the parallel component of the force times the displacement equals force times displacement times the cosine of the angle between them. This is the full equation as written on your formula sheet. And if I zoom in here, I honestly would have written this differently had I made the formula sheet here. Delta E equals the work done. Okay, it makes sense, but when you apply this concept, you kind of want to take this to saying that the net work done, so I'm going to put that in red because it's very important, the net work done on an object is equal to specifically the change in kinetic energy. Change in kinetic energy means the velocity of the object changes. If I take this mass, I'm holding it here, it's not moving. It has a zero velocity, zero kinetic energy. And I move it up. And I do some work. I'm doing work. I'm pushing on it. It's undergoing a displacement, like Mr. P showed us in flipping physics. I just did positive work. But when I'm done doing that work, it's not moving. So what was its change in kinetic energy? What's the numerical value for the change in kinetic energy? Zero. Didn't move. So that means zero net work was done on the object. How can that be true if I did positive work? How can it be true? Someone explain it. Gravity is doing work on it, and it's doing negative work. Good. Very good. So when I push up on it, gravity's pulling down. That's why working out works out your muscles, because you're fighting gravity when you're lifting weights. So I lift up on the weight. Upward force, upward displacement. From gravity's point of view, you got a downward force, upward displacement. The angle between those two is 180 degrees. The work done gravitational force times displacement times the cosine of 180, which as we showed earlier, cosine of 180 is -1. So if I did 10 joules of work doing this, gravity did negative 10 joules of work, which means the object didn't change its velocity. Now if I do more work, the magnitude of my work is larger than the magnitude of the work done by gravity, meaning I exert a larger force upward than the force downward. Then the object's kinetic energy does change. And when I stop pushing on it, it has a change in kinetic energy. And so it has kinetic energy as it leaves my hand, right? That means that the work that I did was larger in magnitude than the work done by gravity. And the discrepancy there, right? Say I did positive 15 joules of work. Gravity did negative 10 joules of work. Well, now the net work is 5 joules. And so the object's kinetic energy will have increased by 5 joules. Make sense? Okay. So yeah, but understand, you cannot, I see this every year, more than one force act, but a student only uses the work done by a single force, and they say that's equal to the change in kinetic energy. Now, if there's more than one force, you got to get all of the work done and add it all together, and that will be the change in kinetic energy. Sound good? All right. So kinetic energy is a type of mechanical energy. Mechanical energy, which we abbreviate as ME. Now, if we're talking big picture, all energy is mechanical energy. If you remember the Science Asylum video introducing the energy, and revisit that if you're a little iffy on any of this, because again, I pointed this out when I showed it. I think that's the best way of introducing the concept of work and energy from a physics standpoint, that Science Asylum video. He showed you that for us, mechanical energy is just kinetic and potential energy. Right? That's all we do. Gravitational potential energy, and I'll talk about in a minute. Spring potential energy. That's all we do. But there's a lot of different kinds of energy that we don't talk about in this class. There's thermal energy. There's chemical potential energy. There's the bonding energies associated with chemical bonds. There's nuclear potential energy that gets released in nuclear explosions or nuclear reactors. All of those energies, though, are either potential energy or kinetic energy. So all energy boils down to, at some point, mechanical energy. But to talk about nuclear potential energy or thermal energy or chemical potential energy involves processes that we just don't deal with in this class. So for our purposes, the only kind of mechanical energy we deal with is kinetic energy, which gets the equation 1/2 mv squared, and gravitational potential energy, capital U, with a subscript G. You might ask why capital U. That's for most physicists, the work done by most physicists, potential energy, any kind of potential energy gets capital U. Sometimes it's a capital V. Have you ever heard of Schrodinger's cat? You ever heard of Schrodinger's cat? In the Schrodinger equation, it's a capital V. More often than not. Not always. But potential energy for us is going to be capital U. And we are going to have two different types of potential energy by the end of this unit. So if we're talking gravitational potential energy, we put a lowercase g. Okay. Now, if this was on level or pre-AP physics, we would give you this equation. We would say gravitational potential energy, I think we even use PE with subscript G, but we don't in this class, is mg times h. Mass times the acceleration due to gravity times the height. And so that would be like an object. And remember, we define the 0 point as an arbitrary point that we can measure our gravitational potential energies from, but you want to choose it usually at ground level or at countertop level, something that's convenient, right? So if we call this the ground point, that's where we measure our height from, then we would say that height is the h that goes into that equation. But again, this is for on level or pre-AP, right? We got to be a little more specific. One thing that, again, that Science Asylum video tried to point out was that the potential energy isn't really that important. It doesn't really tell you that much. Because, again, the point that we measure that we make the reference frames in which we make the measurements of those heights are completely arbitrary. Right? You should be able to describe physics from any reference frame that's not accelerating. So what's really important is not just the energy, but the change in energy as an object undergoes some process, some physical process. So if I start from this height, and then I lift the object up to this height, it doesn't matter where we make the measurements from, we measure the same change in potential energy regardless of the coordinate system that we're using. So we can say, well, we start at some initial position, vertical position y naught, and we end at some final vertical position y. Then I can say, well, the change in gravitational potential energy, according to this equation here, but using our big kid notation as opposed to our little kid notation, we say, well, that's going to be final minus initial. So UG minus UG naught. Well, UG, our final position, is just mg times y, minus our initial position, our initial gravitational potential energy, which is mg times y naught. Well, we can factor out mg out of both of those. And then we get final minus initial position. And obviously, final minus initial position is change in vertical position. So our change in gravitational potential energy as an object moves from one location to another is equal to mg delta y. That is what is on your formula sheet. So the two major types of mechanical energy that we deal with in this class are kinetic and gravitational potential, and those are the equations as they're written on the formula sheet. We did derive this kind of before the break, so I'm not going to go over that. Kinetic energy we actually derive in AP Physics C. If those of you that know calculus, you see squared there over 2. Squared over 2. There's probably an integral there somewhere. But yeah, so if you're interested in, they didn't just make this up, then that's not how physics works. And it's, I bet E equals mc squared. Oh, there's a lot more that went into that. Okay, a lot more. They didn't just say 1/2 mv squared. Sometimes you can experimentally determine a mathematical relationship, but more often than not, you can actually just derive these equations using brute force theoretical physics. All right, there is one other type of energy that we'll talk about. Normally, and I'm going to add this to this unit, because normally I wait until our unit on waves to describe this other type of mechanical energy because it deals with energy stored in things like springs. Why do I wait until waves? Well, anyone that's graphed a sine or cosine function knows that they look like this, right? If you graph y equals sine x, the graph looks like this, and it goes on forever. And that looks like a wave, right? It turns out that waves use sine and cosine graphs. To mathematically describe waves, we use sine and cosine stuff. Okay? The functions, though, not just the sine of an angle, a particular angle, an actual function involving sines or cosines. And you might notice that if I wanted to say plot this guy's position as a function of time, if it's bobbing up and down like this, but I'm doing it as a motion graph, which means the time is progressing on this axis, well, then I get a nice little wave-like graph, right? And so it turns out that the mathematics that describe this type of oscillating motion are the same type of mathematics that describe wave motion. And so usually, in the past, I've waited until our unit on waves before I start talking about springs. We usually mention them a little bit, but we really dig into springs when we get to our unit on waves. We don't do waves anymore in this class, so I'm going to have to throw in spring stuff in this unit. So we're going to extend this unit a little beyond what I originally had planned and have done before. So we will be adding that on after we've had our review of stuff that we learned before the break. Why am I bringing this up? Because there's another type of mechanical energy, spring mechanical energy. Right? If I do some work on this spring, right, I exert a downward force over a certain distance, I have now, just like when I take an object and I raise it up, I've stored energy in the spring. Its kinetic energy didn't change though because I did positive work, but the spring itself did negative work, right? But there's energy stored in it because when I let go, what happens? Yeah, it springs back up. And that's energy, right? If I connect something to it and I put my hand there, I feel it when it hits my hand. There's energy in that thing. The same type of physics in a bowstring. When you pull a bowstring back and you let go, the farther you pull it back, the more energy you store. And when you let go, the more kinetic energy the object gets, the kinetic energy of the object attached to it. So there is a formula for spring potential energy, which I'll throw out right now, but we'll talk about a lot more in a little bit. And that spring potential energy is 1/2 the symbol lowercase k times x squared. This is how it's written on the formula sheet, I think. Yeah. So it's subscript S for spring potential energy, but it doesn't need to be a spring. It could be just anything elastic. It could, in fact, be this ruler here. I push down on it just like I'm stretching the spring, and I let go and it springs back. Right? That obeys the same physical laws, approximately the same physical laws. K is called the spring constant or force constant. That's just a measure of how stiff the spring is. If it's like a shock spring on your car, it's a very high value, very high value. It's very hard to compress or stretch the spring. If it's like this little guy, very small spring constant, very easy. That's a number that's just theoretical. That's just measured experimentally. And then x is just the distance that you displace the spring. Okay. Again, don't worry too much about that. We haven't covered that yet. We will cover that after we've reviewed everything that we've covered thus far. But that will be our third type of mechanical energy. We will add another one when we do our unit on rotation, but it's just going to be kinetic. It's just going to be spinny kinetic. Spinny kinetic energy. That's the technical word for it. Spin. No, it's not. No, it's not, Gavin. Come on. Are you awake? You're trying to be. Okay. Me too. All right. Now, I did point out that when an object goes from a certain height and then reaches, it undergoes the same change in gravitational potential energy, the path that it takes while undergoing that change in gravitational potential energy, it doesn't matter when it comes to the work that's being done on that object by a force, if that force is conservative. Remember when I said that? Now this situation here, and I made the simulation that showed this. If I let both of these objects go, this guy's going to get to the ground faster, obviously. He's not rolling, he's not sliding down a hill. But by the time he gets to the ground, if he has 5 meters per second, and they both start from the same height, this guy takes longer to get there, but by the time he gets there, he's moving 5 meters per second. Because the work done in going from this location to this location is independent of the path that the object actually takes when going from one location to another. Now, obviously, this guy changes horizontal position, but no work is being done by the gravitational force in the horizontal direction. Gravity's pulling down. This guy's moving horizontally and vertically simultaneously, but like we've done before, we just deal with the vertical and the horizontal separately. So as this object moves horizontally this way, its displacement in the horizontal direction is this way, force is this way, zero work being done. The work that is being done is purely in the vertical direction. So as the objects go from this position to this position, if the force that's causing that change in position is conservative, then the work done by it is the same. Okay, so what I like to think when we're talking about conservative forces, the phrase that springs to my mind is path independence. Spell that right. Path independence. And I like to, this is like the small scale case, but if you think, say you got like a star or a planet, let's say this is the Earth, and you take two identical spaceships, and you start them from the same location, and you shoot one out with an initial velocity this way, I won't even label them. And I take the other guy and I shoot it out with the velocity this way. And let's just say that these two objects, due to the force, the gravitational force from this guy, say this guy might move like this, end up moving like that. It wouldn't be like that, but just, bear with me. And then this guy takes a totally different path, but ends up, say, at this location at some different time. They went from some position we'll call A to some position B, took very different paths, covered very different distances, took very different times to cover those distances. The work done by the gravitational force here on each object will be exactly the same if they start and end at the same position. It's path independent. The work done by conservative forces is independent of the path taken by the actual object. Okay? If you're like me, you ask yourself, why is that important? Why is that even a big deal? Well, it turns out, because I told you the equation here, we get this algebraic version, but the calculus version of the equation, from which we derive all these other equations, hinges on the fact that the work done by the forces involved in those changes of energy are conservative forces. So it's very important, very important. If you want a little more elaboration, there's a nice little blurb here in the notes about it. But what you need to know is that conservative forces, the work done by them is independent of the path that the objects take. This object could go straight down. This object could slide down. You can take this object, throw it up into the air, and then another one, drop it. The work done by the gravitational force when both objects start from here and end up here is the same. How can that be? Well, when I drop this guy, positive work is done by the gravitational force, right? When this object gets launched up, upward displacement, downward gravitational force, negative work is being done. And then positive work is being done. By the time it gets to the same height that this one was dropped from, there's zero work. Zero work has been done because it's the work going up is negative, work coming down is positive. They cancel each other out, and so the same amount of work is done, right, in both cases. Probably could have explained that better, but I'm not used to talking this much, and this is going to take some getting used to. So does that kind of make sense? It's very important. Future STEM majors here, conservative force is very important to understand. Very important to understand. So this will be your first little foray into that. In AP Physics C next year, we really hit that hard when we learn the bigger kid version of the work equation and use it to actually derive those equations there. All right. If only conservative forces are acting, mechanical energy is conserved. This is something that you need to know. This is not on the formula sheet. So I'm going to put a red star here because it's very important. If only conservative forces are acting, mechanical energy is conserved. Conservative, conserved? Is there a relationship there? Oh yeah. It's not political at all. Conserved means not changing, right? You want conservation? You want to conserve the environment? That means like environmental conservation. That means you don't want it to change. You want to have the same number of trees, right? So conserved, if mechanical energy is conserved, then that means the total amount of mechanical energy does not change. And the mathematical version of that statement is the initial mechanical energy in a system is equal to the final mechanical energy of that system. And remember when I did this problem, it had been a while since we did Newton's laws, but I did this problem with Newton's laws. Calculate the force down the ramp, determine the acceleration, did a little bit of trigonometry to get the distance down the ramp, and then did kinematics to figure out how fast this guy would be moving when it got to the bottom of the ramp. But then I showed you how to do it with conservation of energy, and it's much easier. Right? When we do it with conservation of energy, I just start from this standpoint. Well, my initial mechanical energy at this point is just my initial kinetic and my initial gravitational potential energy. So I can expand this out into initial gravitational potential plus initial kinetic. And that's going to equal my final mechanical energy. Oh, we're going to hurry. which is our final gravitational, what's our final kinetic. If I release this guy from rest, I start with an initial kinetic energy of 0. If I've defined the ground level as the 0 point, which is the most convenient way to label that, our final gravitational potential energy is 0. And then, well, UG naught is just mg times my initial position equals my final mechanical energy, which is just kinetic, which is 1/2 mv squared. Notice if conservative forces are acting, no non-conservative forces are acting, then every term brought mass to the party, so the mass cancels out. So it doesn't matter. This guy could be 1 billion pounds. This guy could be 1 pound. They have the same velocity when they get to the bottom. If, and this is like the roller coaster problem where it said, there's friction. So instead of having the roller coaster here to have a certain speed later on, we have to actually raise it up. Well, if
Good
non-conservative...
morning, High School. Welcome back.
Oh, come on.
Back. It is 2021. A couple of quick announcements. We have basketball because it's already Tuesday. We have basketball tonight versus the Green Team at the Coliseum. Varsity girls are at 6. Boys are at 8. We have the visiting team tonight. You can buy tickets at the door if you choose to go. We'd love for you to come out. There is social distancing in the seats as well. I heard it's camo night for us, so be advised. Again, welcome back, everyone. We hope you had a great break. Back to
Talk about this tomorrow. He's going to take it the rest of the time.
Seniors, class of 21, it's finally here.